Hello everyone, and welcome to AISC's live webinar, Designing Members for Torsion, presented today by Daniel Linzel. My name is Brent Liu. I am with AISC, and I will be moderating today's presentation. I want to introduce today's speaker, Dr. Daniel G. Linzel, PE and Fellow of AISCE. He is the Volte-Keegan Professor and Chair of the Department of Civil Engineering at the University of Nebraska-Lincoln. Prior to that, he served on the faculty at the Pennsylvania State University. He received his civil engineering degree from Ohio State University and his master's and PhD from the Georgia Institute of Technology. Dr. Linzel has published over 50 refereed structural engineering articles that have focused on research related to protective barrier systems, building and bridge systems, and components under blast and impact load, as well as the behavior of bridges during construction and under service loads and other topics. Prior to receiving his PhD, Dr. Linzel was employed in the private sector where he performed condition and forensic structural inspections and rehabilitation designs of bridges, buildings, and other infrastructure systems. He currently serves as the chair of the Structural Stability Research Council's Task Group 4, which is the stability of metal bridges and bridge components, and he also serves on ASCE's Composite Construction and Bridge and Tunnel Securities Committee. He is licensed as a professional engineer in the states of Georgia and Pennsylvania. I want to welcome Dr. Linzel. Dan, thanks for being here. I'm going to hand things over to you.
Thank you, Brent. Thanks for the wonderful introduction. I guess if I had any corrections I needed to make, I got my undergraduate degree from the Ohio State University. So other than that, I appreciate everything you said. So thanks to everybody that's attending this webinar. And I would like to say good morning, good afternoon, and good evening, because I'm assuming you're all over the planet, certainly all over the country. So I hope this is valuable to each and every one of you. I've advanced this to the first slide of my presentation for the webinar. And I want to give a little history related to how this webinar came about before we get into it. This actually stems from a presentation, a couple of presentations that I gave at NASCC, the North American Steel Construction Conference in St. Louis a few years ago with a colleague of mine. I'll mention his name in a little bit. And it was related to torsion, very similar to this. And I was, I guess, somewhat pleasantly surprised that the two sessions that we presented this information in, my colleague and myself, were very well attended. There were a few hundred people in each of them, so it made me think that there may be a need to take this, make it a little bit more broadly available than it was at the time. So thanks to some assistance from a number of people, here we are, and again, I hope it's valuable. The real intention with this presentation is to change torsion from a four-letter word, as indicated in this slide, to something that hopefully as designers you are not necessarily afraid of if you have to consider it. I tend to believe that that a lot of people are somewhat reticent to consider torsion if they need to, but hopefully via this presentation, when you run into instances when designing steel structural elements where you think torsion could be a concern, you have the means to address it, and hopefully fears associated with dealing with it will be allayed somewhat. So before I get into discussing what I want to talk about today over the next 90 minutes or so, I'd like to acknowledge a number of people. First and foremost is the colleague I mentioned, Chris Mullen, who's at Virginia Tech. Chris and I were the ones that helped develop this talk initially for NASCC and again in St. Louis a few years ago. And I owe a lot of what's contained in this talk to Chris. It was a lot of fun putting it together, and I can't help but thank him for helping out. I'd also like to acknowledge Charlie Carter and Brent. Charlie Carter helped develop some of the materials I'm going to present today, and certainly his contribution to steel design through AISC is monumental. And thanks, Brent, for helping put this webinar together. I'd be remiss if I didn't acknowledge Lou Geschwindner. Lou is a former colleague of mine at Penn State, and he's former Vice President for Research for AISC. Probably a number of you have used his textbook as a reference and as the book that you learned steel design from. So Lou is actually the person that got me hooked up with Brent to get this webinar going. The final two people are two other individuals who developed the materials that I'll be discussing today. First, Paul Seberg, who ironically my career is mimicking, I guess. Paul started at Penn State, ended up at Nebraska, and helped publish Design Guide 9. And I'll mention a piece of software that I think he was involved with, and Charlie Carter helped him with Design Guide 9 and I believe the software. And finally, Walt Schneider. Walt instructs at Penn State periodically, and for what I understand, helped develop the piece of software that I'll be talking about that you may or may not be aware of. So thanks to all of you. So let me get into what I plan on talking about in association with the T word today. Provide a little bit of background, a little bit of information related to fundamentals for torsion of thin-walled open cross-sections. That'll be the focus today. Talk about shear flow, shear center, the different types of torsion that you may encounter, what that means, why do you encounter them, what do they do to the cross-section. Focus a little bit on what's codified in the manual steel construction in relation to dealing with torsion, if you can ignore it. The design criteria, which really translate into an analysis problem. Give you a list of where you can go for more help, and then spend probably the second half of this talk, if maybe a little bit less, giving you an example. And that's a lintel, a relatively long lintel that has torsional loads that both Chris and I think can't be ignored. So, and we'll talk about the tools you can use to figure out what you need to figure out. So let's get into background stuff. I use in my classes when I instruct information from the preeminent source of definitions of things, and really all information, I guess, on the web these days, which is Wikipedia. I think it's somewhat entertaining and also insightful to pull definitions from Wikipedia and pick them apart. So you'll see periodically in this webinar Wikipedia definitions of things. So, and this is the first, obviously. And what I'll do is I'll break them down and kind of talk about what seems to make sense to me and what doesn't. And in relation to torsion, if you read what this says, I think the first sentence is funny. The second sentence makes sense to me, and I'll use the examples at the bottom from the real world as ways, I think, to get this across. So Wiki, they define torsion as the twisting of an object due to an applied torque. So they're using the word to define the word, which I always think is entertaining. As you all probably know, torsion is a twisting moment. It's a force that is applied a perpendicular distance away from predominantly the longitudinal axis, the predominating longitudinal axis of the member, and it leads to behavior in the cross-section that I think is pretty accurately described by the second part of this definition, where you generate shear stresses if we're talking about pure torsion or St. Venant's torsion, as many of you learned it. So in these examples at the bottom of the slide, I think indicate the stresses that can be generated, or what torque does to things. So you can wring out a rag, you generate these shear stresses in the rag, and there goes the water. Removing or putting a tire onto a car, you use your lug wrench, you're generating torsion to take the lugs on and off of the axle. If you remember back to your elementary school days, getting rope burn, that's torque. I used to get that all the time on the playground, so I certainly vividly remember it. I think the picture on the lower right hand, portion of the slide is probably the best depictor of torque and what it does to a cross section. So this is where I'm going to need, if you all have stretched and you are willing, some participation from you. I can't tell if you're doing it or not, but if you put your two fists together and you twist them relative to one another, and you feel what's going on where the fists intersect, those are the shear stresses that are being generated in this cross-section that you created. So this is due to pure torque, twist about a longitudinal axis that runs down the center of your fists, and what you feel between the fists is the shear stresses that are generated. So I think the second half of the definition certainly is appropriate here. And torque, again, is just a twisting moment. So now I want to do a little bit more background, and a lot of what I'll be trying to do with this webinar is if torsion has mystified you, try to relate it to some of the fundamental beam bending relationships governing differential equations that you probably came across when you were in your undergraduate mechanics class, deformable bodies class, whatever you want to call it. So I'll be relating a cantilevered entity that is twisting to one that is bending, as shown in this slide. So if you think back to your mechanics class, the governing differential equation for torque, the variables can change, but it's shown in the lower left-hand corner of this slide. It's the amount of twist, theta, at a certain location is equated to the applied load, T, the length of the member divided by the shear modulus, and the torsion constant, J. So how is that equation derived? So you look at this cantilevered solid round shaft. It's solid and it's round so that we can derive this equation. You don't have to consider some other effects that could occur when different types of cross-sections twist. You may have seen it in your textbook where you had a solid round shaft that is suspended in space and subjected to equal and opposite torques. But as structural engineers, we don't like to see anything that isn't supported, so typically it would be turned into what's shown here. And the way this equation is derived, I'm just going to quickly discuss it, is you look at how theta varies from one end to the other along the longitudinal axis of the shaft. So from the fixed end where it's 0 to the free end, point B is shown in this sketch, and you examine that variation, and you use that in conjunction with what's going on within the cross-section, within some infinitesimal element dA as it's shown here. It's a little rectangle. And you look at how that element is straining due to the loads that are occurring on this shape, and you basically look at changes in the strain that's applicable over the length versus the amount of twist that's occurring over the length. And you have a load that's causing all that, the torque, and you combine all those things, and you end up with this governing differential equation where theta equals TL over GJ. And we typically refer to GJ over L as the torsional stiffness, so it's the inverse as shown here. And I'll use that in a minute to kind of equate it to the right-hand side of this slide. So basically the way the equation is derived, again, look at the variation in twist, look at what twist is doing within the cross-section, the strain that's being created. Here, since it's pure shear, that rectangle is turning into a parallelogram, so the strain is shear strain, which is an angular change within the element. And you combine all those things and to relate the force to the deformation, the load, which is torque, to the strain. You use material properties to do that. That's where G comes in. And you end up with this governing differential equation. The right figure is what happens in beam bending. So this is a figure I had a grad student create. It's not the most sophisticated figure. It's showing a rectangular member. It could be round. But it's fixed on one end. It's got a moment applied on the other end. And the rotation theta that we're looking at here is how much it's rotating vertically, not within the cross-section, not how much it's twisting along the length. But you do things similarly with beam bending. You look at what's going on in relation to how that rotation is changing from the fixed end to the free end, and the strains that develop in an element in the cross-section as a result of this bending. Those strains are normal strains. They're making the rectangle get bigger or smaller. You relate those strains to the load and to this amount of rotation through material properties. You end up with the equation on the right. The reason why you have a differentiation of theta as opposed on the right-hand side as opposed to theta by itself on the left-hand side is, again, because the strain we're looking at in the beam is a change in length, where the strain on the right-hand side, where the strain that we're looking at in the shaft that's twisting is a change in angle. So, but they are related, I think, and maybe that would help to demystify where this torsion stuff comes from. So now I've spent a lot of time talking about that slide, and you're probably wondering, okay, so what? We don't ever design structures that have cantilevered solid round shafts as our main load resisting elements. So now we talk about, well, what happens when you do have sections that you typically design with, which are shown here, that are twisting. You can't ignore twist. What are the consequences of having something other than a solid round bar twist? And obviously things get more complicated. These are thin-walled sections. We're going to focus on thin-walled open cross-sections, but some are shown that are closed, HSS sections. So irrespective, some of the things that you have to deal with get more complicated with regards to their behavior and their response to twist. And that's what I have to talk about later on during this webinar to kind of further elaborate and hopefully demystify some of the things in relation to torsion of steel shapes. So what are the consequences of these sections twisting? You have new things you got to worry about, new terms you need to know. And I'm assuming a lot of you have already heard these terms, maybe many years ago, but you need to know what shear flow means. You need to know what the shear center is and what that means. And the way you calculate what was called the torsion constant may change. You may actually call it something different, and you need to understand how that happens. So left-hand side of this slide on the bottom shows these cross-sections twisting. Right-hand side just is a couple figures that show shear flow and then distribution of stresses in different cross-sections. And you need to understand what can happen when you load these sections in certain locations and how they respond to a load that either directly causes twist or is placed in a fashion on the cross-section that will give you some twist. So we'll talk about those items in a little bit more detail in a minute. And the other thing you need to be cognizant of, if you have a thin-walled section that has torsion that you can't ignore, is you may need to start worrying about warping. You need to understand what warping torsion is and what it can do to the cross-section. So these are a couple sketches that come from one of the references I'll talk about as I end this first section. And if you look at the drawing on the right of this slide, it's an I shape, so you'll see that the top and the bottom flanges are no longer plane under this hypothetical twist. That's warping. That's where plane sections don't remain plane. And if that tendency is prevented in some fashion, either due to support conditions, physical restraint from other elements in your structure, or if it's prevented from natural behavior of the cross-section, you may need to consider the effects of these stresses that could result from this restraint on the behavior of the cross-section, the total stress state really on the cross-section. So we need to have a little bit of a discussion in relation to what warping is. And again, in similar fashion of what I think I just did, talking about the fundamental governing differential equation for torsion, comparing that to the beam bending governing differential equation, moment curvature. I don't think I mentioned that when I went through it first. I'm going to try to relate what goes on with warping to beam bending. And I do this when I teach it. I wasn't the one to come up with the analogy, but I think it's a great one, and it may help you understand kind of what warping is and what it does and what the stresses are that result and how they can be calculated. So, and the final thing in relation to the background portion of this webinar is, so what? So I know you're probably here for the CEUs, PDHs. I certainly understand that. I hope you get something out of this webinar. But when you look at this statement, you're probably wondering if you should just hang up right now and bail on the whole talk, because in Design Guide 9, which is the best reference I think that's out there in relation to designers actually considering torsion in structural steel buildings, there's this statement in section 2.3. So if you read it, the first two sentences say, the steel shapes that you design with are typically poor in relation to torsional stiffness. If they're closed cross-sections, that's different. But with thin-walled open cross-sections, you usually don't get a lot of torsional stiffness, so avoid it if you can. So it makes you think, well, why am I even in here listening to this overeducated numbskull talk about torsion? Well, I'm assuming that you're in here because you may have encountered situations like those that are shown on this slide, which is instances where you can't explain away torsion during your designs. So the left-hand side of this slide is stuff related to steel buildings, which is the focus of this talk. The right-hand side are things that I have dealt with, my graduate students have dealt with in the past in relation to bridges. So I'll talk about situations for buildings that a lot of you are probably familiar with, and then I'll talk about a couple situations for bridges where you can't ignore torsion, I don't think. So obviously on the left-hand side, you all have probably seen a lot of these situations. You could have an instance, upper left-hand corner, where you've got a ledger of some sort, a beam of some sort. It could be a channel. I think these are channels, but they're supporting a roof system. So where they look like bar joists, where the bar joists rest on your supporting beam. You may not be able to load it through the shear center. You may have an eccentric reaction that could lead to appreciable twist that may not be able to be ignored. Now here it looks like it's fully laterally supported, so you could probably argue away twist, but you may have situations where you can't. The picture to the right of that shows a support system for some sort of facade, and the way that system dumps to a member that it's connected to. Possibly there's twist you can't ignore between the tubular sections that are back there behind it or between the column that supports these things. Lower left-hand corner sketch, similar situation. You got some sort of wall system, bearing wall, exterior wall that's dumping to this I shape, not through the web. The resultant force doesn't fall through the web. And then you can have these crazy horizontally curved sections. This looks like it's for a canopy of some sort, where the curvature leads to twist. We run into that a lot on the bridge side. So the right-hand top picture is a horizontally curved steel plate girder cross section. Torsion can't be ignored. Twist cannot be ignored. And in AASHTO, in Part 6, which is the steel members portion of the LRFD spec, there's ways to address it. And then the bottom right picture shows a skewed bridge. And with skewed structures, under certain loads, those loads are not applied at the same distance along the main supporting members, here plate girders. Because of that, you get differential deflection. They're connected, these members are connected rigidly through bracing to form kind of a grillage. This differential deflection can lead to global twist, where the effects thereof lead to behavior in the plate girders that needs to be accounted for. So I'm assuming you run across situations where you can't necessarily, in your mind, convince yourself that torsion shouldn't be considered. And if you ignore it, these are the dramatic photos that show failures of structures. Are they purely from torsion? I would say no, but there's certainly torsional components to these failures. You see this Bailey building, I think it's a rigid frame that came down. And just looking at the pictures, it appears there's some torsional effects, certainly in the beams or the horizontal members in the frame. The lower middle picture is the Marcy Bridge in New York. That bridge came down in 2003, I think. I could be wrong about the date, but it suffered a global lateral torsional failure. That was more of a stability issue, but torsion was a component, and I just show a little shaft that's twisted all to pieces. You're not necessarily going to encounter that, obviously, in structural steel buildings, but torsional failures can occur, so maybe that's why you're in here listening to me. So now we move on to some fundamentals in relation to the behavior of thin-walled cross-sections, focusing on thin-walled open cross-sections. So we'll talk a little bit more about what this shear flow stuff is. We'll talk a little bit about shear center, and then also talk about the different types of torsion. Elaborate a little bit more on St. Venantius pure torsion versus warping torsion and their effects. So let's get through those things, and then we'll talk about design criteria as they relate to AISC and considering what torsion does. And then we'll do an example. So some terms you may or may not know. I've already alluded to these things, but let's talk about them again. Again, I'm going to use a wiki definition because it's amusing in relation to, again, shear flow. I'll show you something on wiki, or from wiki in relation to shear center. And I think that's it. So what's wiki say about shear flow? There's a solid mechanics and a fluid mechanics definition. And in solid mechanics, it says it's a gradient of a shear stress force through the body. Fluid mechanics, it says it's the flow induced by such a force gradient in a fluid. So when you combine these things, I think the sum of the two definitions is pretty good, in my opinion, in relation to what shear flow is. I don't know what a shear stress force is, but if you go back to the fist example, so I'm gonna assume you all are gonna put your fists together. I assume you did it before and twist them relative to one another. I think you may be able to count this as part of your wellness program at the places that you work. So, and I don't know if Fitbits count twisting your wrists as part of the daily step routine, but maybe they do. So anyways, hopefully you put your fists together, you twist them, you feel the shear stress that exists between the fists, and the shear stress direction and effects change relative to the center of twist for the cross-section, and I guess relative to the center area, but they change, and these shear stresses work their way around your fists and flow through the cross-section that your fist creates. There is a change in the distribution of those shear stresses and the way they move in the cross-section, and it's based upon the type of cross-section that you have. So shear flow is evidenced in this slide on the right-hand side by the little arrows that you see in the I shape and the channel and in the Z shape. And notice their directions are different depending upon the type of cross-section you have. And the way they distribute and the magnitudes that those arrows have are a function of obviously the amount of twist that's occurring, but also the type of cross-section that is being twisted. And stuff is flowing. As engineers, I love to say in my classes, we're not very creative. What we use to describe things is what they do. So what is shear flow? It's shear that flows through a cross-section. And it's focusing on stresses. Let's talk about shear center. So if you buy that shear flows through a cross-section that's twisting, again, if you don't, put your fists together and twist them relative to one another. Hopefully that helps you maybe believe what I'm saying. Then maybe you'll buy that you can establish a point within any cross-section or even relative to a cross-section about which all of that shear flow will cancel itself out. So if you load a cross-section through this point and you look at how the cross-section responds, the resulting shear stresses will establish an equilibrium point and you won't get any net twist effects on the cross-section. That's the shear center. And I think the definition shown here from Wikipedia is pretty good. It is a point where shear force can be applied. Is it a shear force? It's a force can be applied without inducing any torsion. Sometimes, depending on the cross-section, it coincides with the center area. Sometimes it doesn't. If you have sections that consist of thin rectangular pieces, in general, the shear center is located where they intersect, but not always. Channel is an example where they don't. And then where do you establish it? The shear center, you look at equilibrium. Where do you get this balance of what's going on in the section when it responds relative to what's being applied to it? It's not always easy to figure out where it is for different cross-sections, but that's already been, a lot of these values have been established and they're available to you in the manual in Section 1, as many of you know. So let's move on to warping. What warping is relative to pure St. Venant's torsion. So thinking back to the round cantilevered solid bar and that equation that we derived saying theta equals TL over GJ, that's pure torsion. The fist twist and the shear stressors are due to pure torsion. And so pure St. Venant's torsion is planar rotation. Everything stays plane, and you generate these in-plane shear stresses that flow. And again, you can locate a point called the shear center about which the force and the responding shear stresses cancel each other out. What's warping? I alluded to it before. Here's the formal definition. It's a tendency of portions of your element to move out of plane when it twists. And if it's not prevented physically, then where it could be prevented physically, no stresses develop. But if it is prevented, either physically or just naturally due to the behavior of the cross-section, you're going to develop additional shear and normal stresses that you may or may not want to consider when you do your design, which I will say in a little bit really boils down to an analysis problem following AISC. So all thin-walled sections want to warp. Thin-walled open sections, the differences relate to how much, and you as a designer need to establish, do I need to worry about it? Can I explain away whether torsion is really happening in my section and whether it's significant? And if you can't explain it away, how do you consider it? So you need to figure out if it should be ignored or not. So thin-walled sections, again, when we talk about thin-walled sections, we're talking about sections whose thickness is small relative to their longer dimension. So I shapes, channels, rolled shapes. That's what I mean by thin-walled sections. So to explain more what warping is, I'm going to use a beam analogy again. And this information is available in DG9 and other sources. And I think it's a good analogy to maybe bring home how warping happens and relate it to beam behavior, I think. So what we're going to do is we're going to look at an I section. This is obviously a section view that's subjected to a concentrated torque. Let's assume the thing's simply supported. So there's supports at either end. We're cutting it right in the middle. We have a concentrated torque applied in the middle. So what you can do is take that torque and turn it into a statically equivalent couple. So we're taking that torque and we're saying it equals concentrated forces applied at the top and the bottom of this I section, equal and opposite, that lead to the same amount of twist. So you take whatever the applied torque is and you divide it by the height of the section. So we're going to start to do that, a statically equivalent system to this concentrated torque. And then what we're going to do is say we're going to look at one or the other of the flanges in plan. So we choose the bottom flange here because that way the arrow is kind of going in the same direction. So we pull out the bottom flange and we look at it in plan view on the right-hand side of this slide. So we have the beam flange. Again, this section is simply supported. So we have reactions, we're saying, at the ends of the beam. Half of that force, this is just the beam flange, the bottom flange being examined. So you got that one portion of the couple, T over H applied at midspan. You do your statics. And you know at midspan you've got moments in shears from this load, which is really part of the torque. It's the torque decoupled. Okay? So if you look at this free body, it's a rectangle that's in bending. So that rectangle is loaded when it's in bending. I'm going to try to draw on my slide here and draw it straight. We'll see how much coffee I've had today. That thing rotates. Boy, that's bad. I'm going to fix that. So the ends rotate. The beam deflects. I'll draw the deflected shape like this. Just hang with me. Okay, looks like it's buckling a little bit. And the ends rotate. So they're no longer vertical. So we have this rotation and the deflection. I'm not even going to try to draw the top of it as bad as that sketch is. But you all buy, I hope you all buy that that happens. Okay, it's exaggerated, but it happens. So plane sections remain plane, but they rotate at the ends. This thing is simply supported, and it's loaded as shown at midspan at the top of this sketch. So if that happens, do you buy that the bending of the ends of the beam equate to the torsion that occurs in the sketch shown on the lower right here? So again, we're looking at the bottom flange, and notice this bottom flange does not remain plane anymore. And we're trying to equate that to what's going on in the beam from this sketch. So that beam is bending. Again, it's just the bottom flange. It's loaded with this force that represents the couple, and it rotates. And again, I'm going to try to do this and make it reasonably straight. I'm not holding my breath. So you get that rotation. And that rotation equates to what happens in the cross section. So if you look in the upper right-hand corner of this slide, I'm not going to try to draw anything else because it'll be a mess. You see on the right-hand side of that small cross section, small piece of a beam where it says warping a cross section below it, bottom flange is kicking in a direction, and the bottom flange is kicking in a direction, and the top flange is kicking in a direction. Bottom flange rotates one way because it's loaded as shown here. Top flange is rotating the other way because it's loaded in opposite direction with these decoupled forces. So hopefully trying to equate what's going on in the flanges to these rectangular sections that are bending may help you understand what warping is doing. And if you look at what's going on in these bottom sketches, and you look at the warping shear stress distribution and the warping normal stress distribution, doesn't that look like what happens in beams that bend? So again, going back to this beam representation, and you look at what's going on with the shear and the normal stress distributions in the flanges, look at those stress distributions in plan. That's what happens in a rectangular beam that bends. So hopefully maybe that helps you a little bit kind of understand what's going on with warping. And actually I want to go back to this slide, excuse me. So, and I want to point out that these sketches come from one of the references that I'll talk about at the end of this first portion of the presentation. I think these are the best sketches that I've seen that compare St. Venant's torsion, but more so really show what happens with warping, what happens to the cross section. And they come from a reference that's related to bridge design, steel bridge design. And again, I'll talk about that when I get to the end of this first section. So that's enough, I think, fundamentals. You will see some more governing differential equations in a little bit, so don't kill me for that. But I have to show you some additional governing differential equations to get to how you would evaluate members when you can't ignore torsion. So let's talk about what we do with this information. So you have a little bit more background. Hopefully it's helped you. But let's talk about now what AISC at least discusses and shows you in Part 16, the spec in relation to torsion. And it really turns into an analysis problem like I talked about before. So I first want to briefly mention how torque is worked into the specification in the manual for thin-walled closed cross-sections, HSS sections, so tubes. Briefly going to talk about this, but I'm going to focus again predominantly on thin-walled open cross-sections, eyes, channels, angles, T's, and if those things have torques in them that you can't ignore, what are you going to do? And what does the AISC tell you to do? So, in relation to HSS sections, well, all of this information is presented in Chapter H in the spec, so the combined loads, combined forces sections. I think it's torsion and combined forces. And in relation to thin-walled closed cross-sections, again, tubes, you see torque in this one interaction equation in Article H 3.2. And torque's considered in the second term in the interaction equation. It's squared, so it kind of gives you some idea about the relative importance of the torsional and shear effects in comparison to the axial and bending effects in various rolled shapes. But it's a standard interaction formula where you're considering the cumulative effects of axial plus bending plus shear caused by various direct shear or shear from torsion, and then the torque. And basically you're adding up what everything is in the numerator in this interaction equation, which is what is required, what's the demand, and then dividing that by the capacity. So R is required, I always say to my students, and C is what you have, your capacity. And you're seeing if it's less than or equal to 1. So torsion is considered, but its effects are somewhat mitigated because it's understood that thin-walled closed cross-sections, sections that are closed, are pretty torsionally stiff. Just to mention the things shown at the bottom of the slide, AISC does recognize if your required torsion that your section must resist, the demand is less than 20% of your capacity, then you can ignore torsion completely in these cross-sections. And there's some equations that are given in an earlier article that help you figure out some things in relation to torsion. But again, my focus here is sections that aren't torsionally stiff, which are thin-walled open cross-sections, cross-sections that are eyes, channels, T's, things like that. So those items are addressed in Article 3.3. And it's basically, this is where I think it's okay for me to say this turns into an analysis problem. So you're doing stress checks. So you're determining stresses, cumulative stresses due to all effects at locations of interest to you as a designer, and you're comparing them to some limits. And there's normal stress evaluations, there's shear stress evaluations, and there's a critical stress evaluation. I'm going to focus on the first two shown here, which are the normal and the shear stress components, and I'll tell you why. You certainly, if you're designing with a section that you're concerned about its torsional buckling resistance, that's certainly something that obviously needs to be a worry to you. But I think Chris Moen and I agreed when we put this together that if you run into a situation where you're worried about the buckling capacity of a section under an applied torque, you should probably attempt to detail the section so that isn't a concern. So try to make the section as compact as possible for twist. And the reason being is that there's been a lot of research that has looked at torsional behavior of steel sections, but I personally don't think, and I think Chris agrees, that there's a lot out there that's been codified that says for the sections that you design, the rolled shapes you design, the eyes, the T's, the angles, what are their buckling limits? So we're arguing that you should try to have these sections proportioned in a way where you're not concerned about torsional buckling, pure twist buckling. And typically the sections that are torsionally weak are cruciform, the weakest are cruciform cross sections, and you don't design with those. So I'm focusing on the first two equations here. But really all three, when you look at it, they're very conservative. They're limiting things to first yield normally. So when you load axially, push or pull on your section, limited to yield, limited to shear yield for shear, and then buckling is some critical stress, more than likely an elastic critical stress. So they're very, very conservative. So this is what the code gives you. It's in Article 3.3, and this is where they talk about torsion and what do you need to do. So there's stress limits. Where do you get these stresses? How do you calculate what the demands are to compare to yield or 60% of yield for normal and shear? That's where Design Guide 9 comes in. And Design Guide 9, along with giving you a lot of the background that I've already talked about, it elaborates a little bit more on how you calculate these demands. So how do you figure out what your stresses are that you're going to compare to yield or 60% of yield? And it's basically superposition. So we're dealing with, again, limiting things, keeping things elastic from a stress perspective, and you're basically adding or combining, I should say combining stresses that are caused by all the possible effects in your steel shape, and you're doing that in a critical fashion. So you're trying to find the location in the cross-section where the additive effects of directly applied axial loads with strong and weak axis bending loads with any directly applied shear loads, where they cause the worst effects. So, so the equations that they give in DG9 as shown here are adding or subtracting normal and shear stresses. So A is axial, BX is bending about the local x-axis, BY is bending about the local y-axis, and W is warping. And if you look at the top two equations, these are for any cross-section. If you notice, all the terms have pluses and minuses associated with them. So you as a designer need to track your signs. You got to track the direction. What is axial causing relative to bending? Where is it in compression? Where is it in tension? For normal stresses, and also for warping stresses. And the same can be said for shear. Now, one saving grace with I-shapes is that you're always going to find a location where all the effects from bending and twist for normal and shear stresses are additive. So there always will be a location where you can just add up the magnitudes for normal and shear stresses. So obviously relative to axial, if axial is in compression, I'm assuming you all would consider it negative, so you need to keep track of that sign relative to bending and twist. But the other terms, you can just add up the magnitudes and then consider those relative to the direction that the axial force is applied. And the same can be said for shear. But for sections that aren't I-shapes, you got to keep track of stresses. And my assumption is, and maybe this is incorrect, that you're wondering, well, how do I do that for sections that aren't I-shapes? So I'm going to go back to this sketch for an I-shape and try to relate it to other sections and go back to this slide. So my opinion is I think you have to revert to just drawing sketches and doing some fundamental examination of the behavior of the cross-section under the twist load. So for other cross-sections, you look at what your load's doing, try to decouple the load as best you can and say, on the flanges, on the main bending resistant elements in my cross-section, what is this torque doing if I looked at that flange, let's say in a channel, or flanges in a channel, how would they be loaded using this simplistic examination? How does that affect the stress distributions in the flanges, both shear and normal? And then that sets up my sign convention to use for these superposition equations. So that would be my opinion. If you're confused about it, draw some pictures. So this is what DG9 gives us. It gives us these equations. And so we have to figure out the stress contributors due to twists. So warping normal stresses, and then direct or Saint-Venant shear stresses and warping shear stresses. So we're going to talk more about that and where those stresses come from with the next few slides. So let's talk about the contributors to the stress states in thin-walled cross-sections, again in I sections, channels, T's, angles, things like that. So this is the governing differential equation. We'll talk about shear stresses first. So we'll do shear for direct torsion or Saint-Venant torsion. We'll do shear stresses for warping, and then I'll show the equation for normal stresses for warping as well. Just a little bit of background. This figure has been shown on multiple slides leading up to this. My assumption was if you're exposed to what shear flow was, you've probably seen this equation. And I'll briefly explain where it comes from in a simplistic form, which will hopefully be acceptable. It's really, this equation comes from looking at what goes on in relation to a relationship between pure torsion and shear stresses in a rectangle. You're calculating the shear stresses due to pure torsion or Saint-Venant's torsion in the elements. So in the rectangles that make up the cross-section that you're designing, independent of each other element or each other rectangle. So you're going to look at, for an I shape, you're going to look at the web, and you're going to figure out what is the St. Venant's shear stress in that web. And it focuses on the material properties that make up the web and the thickness of the web. And this equation is derived, I think, by, again, doing some comparison to what beams do in bending, but I'm not going to get into that. So, but notice that it involves the first derivative of the rate of twist. So to calculate the shear stress component in either or of these equations for S sub V, excuse me. So tau sub T is the shear stress from direct torsion. Okay, you need to have the first derivative of the angle of twist at the cross section of interest. So we're taking derivatives of angles of twist. Keep that in mind. Let me show the equation for the shear stress and normal stress contributors from warping. So these equations look crazy, and I understand that, but there are, I think, the relationships between beam bending. So I'm going to show you that sketch again that looks at the flanges of beam and kind of relating beam bending to torsion. Really are what lead to this equation looking the way that it is, and also what lead to the normal stress equation looking the way that it will look when I show it to you. So anyways, the equation for the shear stress due to warping at some location S in the cross section equals the formula shown here. It involves the elastic modulus, what's known as the warping statical moment, the third derivative of the angle of twist, and the element thickness. So I have to figure out angles of twist and then derive them 3 times. You won't have to do that when we get to the example when I show you some of the tools that are available to you. But you do need a value for a theta triple prime. And where in the world does that come from? So I'm going to go back to the slide where we did this relationship, and I'm going to compare it to the next slide. So it all reverts back to the simplification of our I shape that twists, looking at the flange of a rectangular beam. That beam bends, and you generate shear stresses and normal stresses in the flanges of the cross section because, again, when we equate the flange of the beam to what it is really in the cross section, which is, again, a top or bottom flange, you get this out-of-plane kick of each of the flanges. So you generate these stresses. So in a beam that's bending, shear stress VQ over IT. So the shear in the cross section times the first moment of the area divided by the moment of inertia times the elemental thickness. And the normal stress is My or MC over I. The moment at that location times the distance away from the neutral axis divided by the moment of inertia, or M over S, the moment divided by the section modulus. We have those relationships. So in our flanges, to calculate those stresses, what's causing this moment in a section that twists? It's this load. So it's torque. And your governing differential equation, I'm not going to go all the way back to the slide where I show you theta equals TL over GJ, but the torque can be related to the angle of rotation. So you can take all of those relationships, the basic beam bending stuff that is shown in this slide, right, to the load that causes this beam, which is really a flange to bend, which is a decoupled torque shown in this slide, and then you relate that to twist that the torque causes. You jumble all those equations together, and you end up with, let me find the slide here, you end up with the equation for the warping shear stress. So this comes from relating what's going on in the cross section when it's twists to the flanges acting as independent little rectangular beams that are bending. So that's the shear stress equation. For the normal stress equation due to warping, this again falls out of this saying your flange acts like a beam that's bending. The load causing that beam, I'm putting my fingers up in quotes, you can't see it obviously, but the load that's causing that beam to bend is a torque. That torque leads to twist, theta. Combine it, normal stress, My over I, what's our moment? It comes from the torque. Jumble those things together, and you end up with this equation where you introduce another geometric parameter, which is the normalized warping function at the location where you're interested in calculating things. So the warping statical moment and the normalized warping function are what fall out of combining all these things together, and they're geometric parameters that can be calculated for each rolled shape. in AISC. So this particular formula involves the second derivative of theta. Again, remember that the last one involves the third derivative of theta. You see when we relate shear to bending how you have this derivative relationship for warping, and then the Saint-Venant's or pure torsion term involves the first derivative of theta. So like I talked about a little bit ago, I'm assuming nobody here would want to calculate first, second, or third derivatives of theta. And this is where Design Guide 9 comes in as an aid to you to help you figure out what these stresses are and calculate them when you need to. So I'm going to do a little bit of discussion about what's available in Design Guide 9 and the appendices. There's 2 sets of appendices in DG9. I'll show you some examples. I've got one more simple little discussion point in relation to behavior of sections that warp. The most simplified way to look at an analogous thing that involves beams and bending. I'll show you a reference list, and then we can move on to the example. So this is what's shown in Appendix A of Design Guide 9. So what do you do? And I'm listing this as analysis because, again, your goal is to calculate stresses. So I consider that an analysis problem. You may disagree with the terminology, but that's what I consider it. So Appendix A. What Appendix A contains is torsional properties above and beyond those that may be available in Section 1 of the manual. So we're blowing up part of this appendix, and it shows the polar moment of inertia. Again, we're talking about non-solid round bars, so we have to use an approximation of the torsion constant. We're talking about the warping constant. There's this additional parameter A that I'll speak to in a little bit. Then there's the additional warping geometric parameters that I discussed before, the warping statical moment and the normalized warping function, and they provided statical moments over here as well. So you have these properties available to you when you need to calculate stresses. That's Appendix A. The second appendix, Appendix B in Design Guide 9, then gives you a bunch of plots of variations in the angle of twist and its first, second, and third derivatives for various combinations of loading and boundary conditions that are shown in the upper right-hand corner here. So I'm showing this for case 2, and this is where you have warping restraint, twist and warping restraint at the ends, and concentrated torque applied. So we're looking at the variations again in the angle of twist relative to the length and its first, second, and third derivatives. And this is just one example. There's a bunch of them shown in the back of Design Guide 9. So I'll blow up the first plot there for case 2. This sketch shows you what you're considering. There's a little verbal discussion over here. Okay, talks about what the boundary conditions are, and you see this variation. Basically, the y-axis here is the answer to this equation. So what you get out of this particular figure is a number that equals what's shown in this equation. And when we do the example, I'll show you what that means. The x-axis is where you are along the span. So you can use these functions to figure out what you need to figure out in relation to theta here on this particular diagram, and then its first, second, and third derivatives. These plots differ based upon the quantities L over A, where L is the span length that's shown in lowercase here, and A is this additional geometric parameter that is shown in Appendix A. So lowercase a is shown here. It basically was derived to use with these plots, these nomographs, these figures, whatever you want to call them. So it was derived to allow you to use these plots for all of the rolled shapes that are given in Appendix A. So it's basically a parameter, I believe, that addresses kind of the torsional stiffness of the cross-section geometrically. So we'll talk about, when I get to the example and we calculate one particular number, how to use this table for one value that you would need to get stress in a little bit. So that's what's available in Design Guide 9. And again, we'll come back to that when we get to the second part of this webinar, which is doing an example where it could be argued you need to examine twist and its effects on the behavior, an analysis problem, the stresses in the cross-section. So one other thing I want to briefly point out is if none of the explanations I made in relation to warping and its effects on a cross-section that twists make any sense whatsoever, There is stuff that's provided in DG9 and elsewhere that just makes it as basic as possible, I think, which says if you want to figure out the stresses in your I shape, then do what's shown here for the shear stresses in a flange and the normal stresses in a flange due to warping. So this basically is saying it's equating what's going on to a rectangular beam and bending. If you think about how you figure out stresses in a rectangular beam that's bending, it's 1.5 V, that's the applied shear force, divided by the area of the cross-section. Normal stresses are M over I or M over S, focusing on the flange. That's what these formulas represent. F stands for flange. So if you want to figure out the stresses in an I shape that's twisting, you can use these formulas if you want to not have to go to the first, second, and third derivatives and get a reasonable approximation of what's going on that could be interpreted to be conservative. So you can do that if you want. So I wanted to point that out. So the last thing I'd like to point out before I get to the example is just some sources of information that that you may or may not be aware of that could help you when you get to a point where you think you need to address torsion. So the first two that are listed for buildings are obvious, I would think. DG9, which is what I've been talking about a little bit, and obviously your manual. That's where you find the codified information. In DG9, it gives you, again, gives you more background and additional aids that can help you do this. I do want to point out a couple of sources from the bridge side of the street that may be beneficial to you. There's a document that's published by the National Steel Bridge Alliance in conjunction with AASHTO through one of their collaborative groups, one that I work with. And it's called the Guidelines. It's the Guidelines for Steel Bridge Analysis. It was published, the gentleman that did most of the work, his name's Dominic Coletti. He works for HDR over in North Carolina. And there's a lot of discussion in that document that may be beneficial in relation to understanding what torsion does that could supplement some of the things. So you need to be aware that you can go get that from the web. It's available for free download through AISC, and it's a very beneficial document to have. The figures that I showed that I stated, I think, are the best ones I could find that detail what warping does in relation to direct torsion and the corresponding stresses from both of those effects come from the AISC NSBA Steel Bridge Design Handbook. The figures come from an older version of the handbook than I think was available online, but still that link will get you to additional discussion about what's going on in these cross sections. The version where the figures are in is one where they're housed, I think, in Chapter 12, if I remember correctly, and it deals with horizontally curved cross sections. So that's something to keep in mind as well. And then just general resources. I think the best source of information in relation to steel structural element behavior is Salmon Johnson and Malhas. That textbook. If you have cross sections where you got twists that aren't standard shapes, then I want to push you to Rourke's Formulas for Stress and Strain, and obviously your undergrad books are of interest to you. So I think we're going to keep rolling right into the example, and then at the end of the example, if there's time, I'll take some questions from people. So here's what, and again, this is why I'm assuming you're all here. Hopefully you're all still conscious and ready to look at what we're going to do here. So here's the example we're going to examine. This is just a steel lintel beam spanning an opening in a bearing wall. It's supporting, as shown on the left-hand side, the section cut. It's supporting a CMU wall, but it also has a facade that's dumping load to that I shape. We're using an I shape here that causes twist. So you have a section cut. You got the elevation view. This is a long span lintel, 15 feet. There's live load applied to the roof of this thing. But when Chris and I put this presentation together for NASCC and VR discussions and Chris's discussions with Jake Lamb, who should get some props for this because he provided the example to Chris, we kind of decided, Jake agreed I think with Chris, that we could argue that the live loads applied to the roof would be arched over the lintel. You may disagree, you may think we're full of it, but for the sake of the example, we're just including dead load. And really, if you included the live loads, those would just be additional stresses, additional loads, I should say, that would lead to more demand on the cross-section. The process is going to be the same. So this is what we're looking at. You see our triangular area of influence here. So we're looking at that triangle, and we're going to simplify the dead loads that are applied directly to the section and those that cause twist as uniform loads. So again, the process is largely the same. So let's talk about what you do. You define your structural system, how long it is, which I talked about, boundary conditions, what the materials are. You find out what the demands are due to loads that cause direct shear, they cause vertical bending, that's what I'm calling the moment M. They cause torsion and any applied axial loads. You have to calculate the angle of twist from the torsional effects and its derivatives, and then you use the equations from DG9 to calculate or superimpose and determine the cumulative bending, torsion, axial components to the normal stresses, and then the components to the shear stresses. And then you add them up. So we're going to go through this process, and really probably the biggest component of this process, obviously you have to define your loads and make sure you know the span right, but one of the biggest components, especially in relation to twists, are adequately defining the boundary conditions. So I'll talk about those a little bit. So let's discuss the boundary conditions now. I forgot I was going to do that. So first of all, we'll select a cross section. So typically you want to select a cross section that's about the same depth of the course of CMU that you're supporting. So we're going to use an 8-inch deep cross section, W8, and we just selected a W8 by 24, 50 KSI, 15-foot span. So these are some details that show the support conditions for this lintel. So I think if you look at the elevation view, you could argue that it's simply supported. So we're going to assume pin-pin for vertical loads, pin-pin for shear, direct shear, and for vertical bending moment. But then you wonder what's going on with respect to twist and what are the support conditions with respect to twist. The boundary conditions that you define directly affect the resulting stresses in the cross-section, especially warping stresses. So you really got to pay attention to how you're going to define these boundary conditions. And I'll talk about that in 2 slides. But start thinking about what you would do with this particular lintel from a twist restraint case at the ends. So let me talk about a couple of quick little simplifying assumptions that are made with this example that are conservative, that you may or may not agree with and may or may not want to make. So for the sake of this example, we're going to go ahead, even though you see a shear stud here, we're going to assume that we have a non-composite lintel with respect to the masonry above. And that's a conservative assumption. That assumption's really being made with respect to twist. So the twist that's caused by this facade as it dumps to the lintel. Again, while there's been a lot of research looking at torsion of sections, how torsion affects, directly applied torsion affects stress distributions in rolled shapes that are then composite with something else, there hasn't been a lot of work done with those sections that I'm aware of, and I don't think Chris is either. And so we chose to ignore composite action, which would be a conservative assumption. You get higher stresses than you normally would. So, and one thing we're also ignoring, even though it isn't stated here, is if there's other framing that's going into this eye shape from something else, would that framing restrain twist? It could, but we're again, for the sake of this particular example, saying the facade is causing loads that make the thing twist and nothing's preventing it, which again would be conservative. So now back to the boundary condition discussion. So let's talk about this for a second. So again, we have our section shown here. You've got the facade causing a twist load. You've got the CMU dead load causing a directly applied bending moment. We're going to simplify those loads as uniform loads. I'll calculate them in a minute. And let's talk about the boundary conditions. So I think, again, I would believe you all would agree with me when I say we can assume this thing is pin-pin for vertical bending due to the directly applied load from the CMU plus the vertical component of the load from the facade. And I would assume you all know if we do this relative to this, so we assume it's simply supported for bending as opposed to making it fixed for bending. That obviously affects the deformations, the rotations, and the corresponding stresses where pin-pin, no bending stresses at the support, fixed, you generate bending stresses at the support. So let's compare that to torsion. So we have torsion, and we're showing pin-pin for torsion. We will come up with loads that will be a uniformly applied torque TU along the length of the member versus fixed for torsion. So we need to talk about what twist pinned and twist fixed means. So for this particular lintel, since it's supported along the full width of the bottom flange on the CMU upon which it rests, there's no twist there. So even when we define something as torsionally pinned at the ends, that means that there's no twist occurring. These boundary conditions really relate to what goes on with respect to warping. So when we say twist pinned, twist fixed, at the supports there's no twist. So there's nothing going on at the supports where the section is being allowed to twist. But what does twist pinned or twist fixed mean with respect to torsion, or with respect to warping, excuse me? If we define something as twist pinned, that means that warping is unrestrained. So the section can move out of plane, and there will be no stresses developed at those ends due to warping. It's not prevented, so the flanges can move and there will be no stresses generated. If we call it twist fixed, we're implying that there is warping restraint at the ends and stresses are generated. So I think that could be evidenced based upon these two plots that are shown for the case that we have. So these come from Design Guide 4, and it's case 4 in Appendix B, the second appendix. And you look at what's going on. This is the variation in rotation for twist fixed, warping free. So twist restrained at the ends, no twist at the ends, but warping is allowed to happen versus twist fixed, warping fixed. You see the sketches up above. Twist fixed, warping free, notice we have this nice higher order curve. It kind of looks like a deflected shape for a beam under vertical bending. When we have warping fixed, notice now there's a higher order component to the curve where it becomes compatible with the ends and theta goes to 0. This change in the curve is a function of the warping restraint at the ends affecting the rotation. So you have to be really cognizant of what you call things twist fixed, twist free, and what that does to warping. So for this particular example, we're going to go ahead and assume that we have this case, twist fixed, warping free. So if you look at the detail, we'll see it again in a minute. Hopefully agree that that's a valid assumption, because I certainly couldn't tell from what I had with regards to this detail if there was any known restraint of warping at the ends of the lintel. So let's go ahead and do the example, and I'm going to introduce tools to you, and we'll talk about how we calculate things. So again, we're back to this sketch, 15 feet long. We have the influence area here. We turn it into an equivalent uniform load for the facade and for the masonry. Notice that their unit weights are proportional, 40 PSF versus 60 PSF. So you calculate those loads. That's pretty standard stuff you find in the area under the triangle. And use that information to calculate the factored demands on the section from direct shear and bending. We're just considering dead load here, so our load factor is 1.4. And you calculate your bending moments, your shear, at the end, and your bending moment, maximum of which would occur in the middle because it's simply supported. Again, we have pinned as shown in the upper right-hand corner for a moment with the uniform load. And we're going to have, again, torsion, twist pinned, which means torsion's held still at the ends, but warping is not. So this stuff I think is pretty straightforward. There's our demands for the directly applied load from the masonry and the facade. This is a typo. Again, snow would be a load that we would be considering to be arching over and around the lintel for this example, so it's not considered. So you can cross that out. Okay, so we're focused just on the dead load. All right, so these are the directly applied loads, the cumulative effect of these two leading to shear and bending. Let's talk about torsion. So we've arbitrarily, and I don't think it's somewhat arbitrary, but we're basically saying that this facade load is applied at an eccentricity of 8 inches relative to the center line of the web. So that load not only led to vertical bending, moment and shear, but it also leads to twist. So we take our facade uniform load, again we're approximating as a uniform load, and we are multiplying it by the eccentricity, so you get this uniformly applied torque. The torque is the distance away per foot. So that's little tu. That's why we're showing it as little tu. Okay? So again, let me look back. I just received a question about detailing for twist-free bounding conditions. So I'm going to go back and look at this sketch real quickly. So this is a plan view of the lintel. And you notice it butts up against block, it appears. It really depends how you define whether you have restraint or not restraint or warping is based upon whether you think the section for this particular case is bearing up against something. That's physical restraint or warping in my opinion. So So I think you need to look at your detailing. Can you justify to yourself that my section is butting up against something where it's stiff enough where it will prevent out-of-plane movement at the supports? But that doesn't necessarily mean you can ignore warping stresses altogether in this lintel, and I'll get to that in a minute. So back to our calculations. So we calculated VU, MU, and TU. TU is a uniform, we're simplifying it as a uniform load across the length of the section, TU shown up here. So now we got to get to figuring out these stresses, okay? So we have to figure out the stresses due to the moment, due to the shear, and what the twist does. So how do we do that? How do we calculate the angle of twist and its derivatives to give us the shear stresses and the normal stresses that I talked about a little bit ago? Well, you can use Design Guide 9, or you can use another tool, the software package known as WinTorque. So WinTorque's been out for a while. It was produced back when DG9 was created, so I'm assuming this is back in the 80s, I'm assuming, back when Windows was brand new. And it hasn't been updated to the best of my knowledge. It's still version 1. In fact, the version I have I think says version 1. So you can get it. You can get it from steeltools.org. You can get it from other locations, and it's available for free download. I will tell you that if you're running Windows 8, when I installed it, you get these DLL errors that show up, and you abort, do you retry, do you ignore? I would go ahead and retry it. If it doesn't work, then ignore it. And it will still install. So to find the program, you should go into Program Files and look for the WinTorque folder. It could be in the Program Files folder or in the Program Files where it says x86. And in the WinTorque folder is an executable. Create a shortcut and it'll work. That's what I'm running here. And I'll show you how to use it when we get to calculating stresses. So WinTorque is available for you for free download. It goes through calculating the angles of twist and their derivatives along with stresses. Let's talk about how we calculate stresses. Again, we have direct bending, MU and VU, so we need to figure out from the moment how does that contribute to cumulative stresses, normal stresses, and then we have twist. Let's talk about the normal stresses first. So the bending stresses, the demands from bending, and then we'll talk about it from twist, and I'll show you how to use Design Guide 9 along with this tool. So then bending normal stresses, we have bending about the local x-axis of the cross-section. It's MC over I. You end up with 8.5 KSI. I'm not going to belabor that. So that's one contributor to this formula. We don't have any directly applied axial stresses. We only have bending about the local x-axis, no weak axis bending, and we got to figure out what warping does. So there's the strong axis bending contributor. Let's look at warping. Oops, excuse me. Let me back up. So again, we're only concerned about sigma bx and sigma w here. This was the formula I gave you a while ago that discusses how you calculate warping normal stresses. And notice we need, again, to reiterate, we need the modulus. We need additional geometric properties, the normalized warping function for the cross-section, and we need the second derivative of theta. So as I stated before, in Appendix B, this is case 4. This is, again, a twist pin case. Torsion is restrained at the ends. Warping is unrestrained. That's what we've decided, or I decided in relation to this lintel, and it's uniformly loaded case 4. There's the plot for the second derivative of theta for that case. So if you wanted to use DG9, you didn't want to use the software, how would you use this plot? So it's shown on this slide. So I'm going to kind of work through this slide, and the calculations are shown down below. So again, we have case 4. There's the sketch, pin for torsion, uniformly applied torque, lowercase t. And the answer that you will get out of this plot, following these arrows, I'll discuss that in a minute, is what this formula shown up here equals. So the number equals that. And to solve for theta double prime, you must then divide your answer by this value, which is G, the shear modulus, J, here the polar moment of inertia, divided by the load. This is not the thickness. This is the load that corresponds to the sketch. So what do? Given how this section is supported, it's simply supported for twist. You look at the variation in theta shown here. The x-axis is where you are along the span, non-dimensionalized, the fraction of the span length. Notice that theta double prime does not go to 0 at mid-span. It has a value. That is representative of a natural restraint of warping that occurs in various cross sections when they bend. So what happens is it's really due to, again, compatibility or continuity. Out at mid-span, you've got this section twisting. For the twist to be continuous, there's got to be some point at which twists in opposite directions become compatible. That's a natural restraint of warping. And it leads to a non-zero theta double prime. So at mid-span, where we have our maximum vertical bending stresses, sigma bx is maximum mid-span, we have non-zero theta double prime. There are warping stresses that should be considered in your calculations, and we need to determine what they are. So you pick the case that you think is appropriate. You enter the x-axis. You determine the location along the span where you're concerned about. Here we're looking at maximum vertical bending, sigma bx coupled with warping. You enter the chart and you go up to the appropriate curve, or you interpolate between the curves for different L over A values, which is shown over here. L is shown in uppercase here because that's the way it was in the example. In Appendix B, it's shown lowercase. But you take the span, you divide it by A. The units for both of these are in inches. We converted 15 feet to inches. It's 4.11. So you enter the chart, go up to 4.11. You might need to interpolate. You go over to the y-axis, and that gives you the answer to the equation shown at the top. So to solve for theta double prime, you go ahead and solve for theta double prime. You plug in G, you plug in J. Polar moment of inertia, that's from Appendix A. You plug in the torque load. This would be kip feet per foot. That's a units error. Fortunately, cancels out, but that's a units error. You solve for theta double prime. So that's how you use these plots to get your first, second, and third derivatives for the angular rotation. Now I want to go ahead and show you the tool here. So I want to share some software here. I want to share WinTorque. I've got it fired up, and I want to show you how to use it. So there's WinTorque. I already had it open on my machine, and I want to show you how to use WinTorque to get the answers, this one answer that I just showed you, and answers for the other derivatives of theta that you will need for the shear stresses. So what you do is, again, you install this, you find it, you get this window. I apologize for being so small. That's one of the downfalls of using this older program. But you choose Auto Input here. And you can give it the file name, a title. You can do all that good stuff. You can give it your name. I'm not going to do that for the example. But you give it the information that will show up in the header for the output files. You click Next. You choose the corresponding load type. So we have uniformly distributed torque. That's what we simplified it as along the entire member length. You choose the appropriate support conditions. So I'll show you fixed fix, but we chose it to be pin for twist. You choose the span length, 15. You choose your load. Notice the units, 0.14, excuse me. Foot kips per foot, or kip feet per feet. I can't say that. You click Next. And then you have a menu of cross-section. You can choose various rolled shapes. We have a wide flange, and I'll choose 8 by 24 here. Let me find it. There we go. And you see the section properties show up. Now I will mention that this is an older version. Again, I should say the software is based on older information from Part 1 of the manual, so some of the section properties may change a little bit, but it does give you values that are certainly very close to what they are now. So you click Finish. And then you go ahead and run the program. So you click Run. It says it works. And then to look at the output, you click View. And you click on Output. It can give you what you input. If you have a problem, you're concerned about things, you click on Output. And you have options. You can create an Excel file or a text file. Since this is such an old version, or since this program was developed so long ago, I am of the opinion, and so is Chris, that you create a text file. So you hit Create Text, and you will then see your output. And it'll create 2 files. So you hit Create Text, it'll create the files. I'm not going to do that because I already created the files. So let me go ahead here and show you what the resulting output files are. So I'm going to click Cancel here. So that's how you run the program. 2 output files are created. So I hope you can see the first output file. Brent, let me know if you can see it, and I believe that you can. So you have 2 text files that are created. The first one, which is the input file name, shows you at the bottom all of the resulting angles of twist for that loading and boundary condition case that you examine, plus their first, second, and third derivatives. So it gives you all the thetas, theta primes, theta double primes, and theta triple primes. Okay? The second file that's created gives you, and it is the file input file name with the number 2 on the end, gives you stresses, flange shear stresses, web shear stresses for your cross section. And so we're going to work with theta prime, theta double prime, and theta triple prime, those values from wind torque. But you can see where the information comes from. I will say that it's the stresses that you get, there is some instances where the warping components are ignored. So that's why I'm going to work with the values of theta double prime and theta prime, theta double prime, theta triple prime. So again, going back to the presentation, we got theta double prime from the Appendix B in DG9. If you compare it to the output for this case from wind torque, you end up with the same number. Then how do you use that to get the stresses? Now you're plugging it into the equation for the warping normal stresses. Again, this is a formula I showed before. Theta double prime comes from either DG9 or wind torque. Plug in your modulus, plug in your warping, normalized warping function, theta double prime, and you get 9.5 KSI. Since we're working with a W-shaped twisting, an I-shaped twisting, if you remember, the equation allows you to superimpose the warping and bending effects. If you don't have that type of cross-section, you need to chase signs. So we add them together here. So we have our vertical bending component and our warping component. Notice how large the warping component is for this torsionally weak cross-section. We end up with 18 KSI for our cumulative stress effects. Now that we have that, we compare that to the limits from Chapter H of the spec. So we're looking at, again, yielding under normal stresses. Could you consider buckling? My argument is, and again, Chris agrees, that try to do what you can to ignore to proportion your section away from having a twist buckling problem. So we're focused just on the normal stresses. 50 KSI steel, you reduce it, and you compare it to your cumulative stress effects, normal stress, vertical bending, and warping, and you get 18 KSI, and the section's okay. Let's talk about shear stresses quickly. So we've done the superposition of the normal stresses due to direct bending and due to warping. And we focused on what was going on at the extreme fibers in the cross-section, the flanges. And if you remember back to the warping sketches that I showed you, all that behavior happens in the flanges. What about shear? So again, DG9 shows you superposition of shear stress effects, direct shear relative to the local X and local Y axes, St. Venant's or pure torsion shear stresses, and warping shear stresses. So what do we need to worry about with this section? We have to worry about direct shear from the vertical loads, VQ over IT. So that's a standard calculation. VU we calculate is 3.9. I'm not going to belabor this, but it ends up a little over 2 KSI. And we're focused on the web here. I sections, most of our shear resistance is in the web. And what we're going to do is we're going to calculate torsional shear stresses in the web, add those to our direct shear stresses in the web, and then we have to compare those to other elements in the cross-section and what their shear stresses are to get a critical total shear stress. So remember, with I-shaped shear, you focus on typically the web and element. That's your main shear resistance due to direct vertical loads. So we have to figure out what the cumulative shear stress is in that rectangle and compare it to the cumulative shear stress in the flange rectangles, which is the highest. That'll be the total shear stress that we compare to our limits, 60% of yield. So we have vertical loads leading to direct shear, 2.23 KSI. What else do we consider in this cross-section? We consider direct effects from pure torsion in the web. So you can remember this equation, we focus on each element as an independent rectangle. We're looking at the web here. That's why we're looking at T sub W. And it involves the first derivative of the angle of twist. This is from DG9 for case 4. This shows the variation in theta prime from one end to the other of this twist pinned, uniformly loaded with a torque beam. And notice that the highest values for theta prime are at the ends. That's where the highest vertical shear is for a simply supported beam. So that's where we want to superimpose effects. We check the web. What is that total shear stress? We check the flanges. Whichever gives us a high shear stress is what we compare to our limits. So we have the direct shear. We have tau by, 2.2 KSI, give or take. We're going to look at shear stress from direct torsion, pure torsion. So you can get that information from Appendix B for DG9. This value comes from wind torque. Again, the output gives you variations in theta prime. We're looking at the critical location along the span, the end. It's 1.7 times 10 to the negative 3. We multiply it by the shear modulus, by the thickness of the web, and by theta prime, and we get 4.67 KSI. So in the web, our cumulative shear stress effect is 2.23 tau by plus 4.67 for the direct torsional effect, about 7 KSI. So that's the superposition in the web. Now we need to look at what's going on in the flanges. What are the shear stresses in the flanges, and whichever of those two is the highest is what we compare to 60% of yield. Let's look at the flanges. Well, again, the flanges are where the warping occurs in this I section. That's where the stuff kicks out of plane if you think back to those sketches that I kept showing. So this equation involves the third derivative of theta again, and SWS, as well as, which is the warping statical moment, as well as the elastic modulus and the thickness of the flange. This is the plot for case 4, this particular case, in Appendix B for DG9. Notice theta triple prime is the maximum at the supports. That's where we have the maximum direct shear. That's where we're interested in what's going on in the flanges. So you can use this plot from DG9 to get theta triple prime if you want, or you can use wind torque to get it. So you run wind torque, you look at the variation for theta triple prime, where is it the greatest, where is it the greatest, and you calculate it. So you plug these things into this formula. If you calculate these values, elastic modulus, the warping statical moment from Appendix A in DG9, this value supplied by wind torque, we know the thickness of the flange, you get 0.45 KSI. That's the shear stress from warping in the flange. Very small compared to, well, small compared to the other ones. Again, in the flange, we have to add that to what torsion is doing, because if you think back to the fist twist, there's shear stresses in plane all over the cross section due to the twist. See the shear flow. You have to calculate what the direct effects are from pure torsion with shear stresses in the flanges. You need the shear modulus, the flange thickness now, the first derivative of theta. Same plot we used for the torsional shear stresses in the web. All that's changing is the thickness, and we plug the values in and calculate, let me get here, calculate tau sub t in the flange. So again, this is theta prime from DG9 Appendix B for this case, case 4, or from wind torque. Plug everything in, you get 7.62 KSI. So you're comparing, this is the cumulative stress in the flanges, torsion, pure torsion, warping, it's about 8 KSI. If you look back to the web where we calculated shear stresses from direct shear, adding to those the pure shear stress, pure torsional shear stresses, it was about 6.9. And so we have 6.9 versus 8. We take the maximum of those two. We're going to use 8 KSI here. We compare it to our shear stress yielding limit, 60% of yield, and that's 27 KSI. We end up with it being acceptable. 8 KSI is what we calculated. 27 KSI is our limit. So this section is acceptable both for normal stresses generated due to warping, natural restraint of warping at midspan, and then shear stresses in the flanges and the web from torsion, as well as in the torsion and direct shear in the web, and torsion and warping in the flanges. So this kind of ends the process. Again, we went through these steps, and we calculated our demands after we defined the span and the support conditions, obviously the materials and the loads. We calculated the demands and their effects on the normal stresses and the shear stresses. And that ends the second half of the presentation. So what I would like to do, I'm showing you a bunch of references here. A lot of the stuff that we took came from web pages. Just for completeness, I'm showing where all of those are. Again, the references shown at the top here are very similar to the ones I talked about before for the second half. And really, I think now I'll turn it over to questions, but I know I'm over time, so I don't know how Brent wants to handle that. But I thank you for your attention, and hopefully showed you at least a couple of tools that you may or may not be familiar with that can help you address this problem if you need to. So,
okay.
Brent, I'm handing it over to you.
Okay. Thank you very much, Dan. We are pretty much out of time, but we're going to try to address a few questions here before we wrap up.
Okay. I apologize for going over to everybody. That's what PhDs do, I guess.
I just wanted just to echo what Dan mentioned in the presentation today. The WinTorque program is available at steeltools.org. It's a free download. And then I also want to mention that Design Guide 9, if you're a member of AISC, that is a free download from our website. So if you are a member, we certainly encourage you to download that for free. A couple questions for you, Dan. I want to go to slide 46. I'll take a second.
Yeah, go ahead and do it.
Okay, so slide 46. The question is this: why did you choose pin and WinTorque, but on slide 46 you show it to be fixed free?
Showed it to be fixed free on slide 46. Can I choose 46?
It should be up on your screen.
Okay, we're there. So, okay, so let me re-explain the slide if that's okay. So we have two possible boundary conditions that were felt to be appropriate for this particular lintel example. One would be where at the ends torsion is prevented, but warping is allowed to happen, which is this first sketch, the left-hand sketch at the top. The other would be where both torsion, so twist, is prevented along with warping at the top. So you have pinned, and you have fixed for twist. And again, the pin implication is that twist won't happen, but warping is allowed, versus the fixed case where twist won't happen and warping won't happen. And I'm going to go ahead and change slides here, Brent, if that's okay. So going to this particular sketch, which is a detail showing an elevation view and a plan view of the lintel at the ends, if you can argue that there's no gap and you can guarantee that that gap is going to stay closed between the ends of your lintel and what it's butting up against would be CMU, then you could probably argue that, slide 46, you could probably argue that you would have this case where at the ends of the beam, not only is twist prevented because it's sitting on block, but also out of plane, any type of out of plane displacement due to warping is also prevented. Since we didn't have any more information, we thought it would be more appropriate to say, even though the sketch appears to show this is butting up, we're not sure we can guarantee it, and we're going to go ahead and use a boundary condition case that is shown here where, again, twist is prevented because it's resting on block, that I shape, but warping is not. So I hope that answers the question.
Okay. I'm going to take us to slide 54.
Okay.
The question is, in calculating F sub n,
yeah,
why is it that the St. Venant stresses are ignored? Usually this is accounted for in section F2 of AISC when calculating the critical moment.
So the St. Venant stress effects on normal stresses. I think that's what the question is. I think. So St. Venant's, which is pure torsion, as it's commonly defined, implies that when you twist a cross section, you have a planar response. Plane sections remain plane, but you generate these in-plane shear stresses. So pure torsion traditionally is assumed to generate shear stresses only, and so no normal stresses would be generated. So really, when you have warping, well, let me back up. If you have pure torsion, I don't know how to. There's the normal stresses are accounted for when sections warp via the simplification I talked about, where you equate elements of the cross section to a beam, and that's where the normal stresses show up. And they are caused by twist, but they are reflected in the warping response of the cross section. So sigma W is what picks up when cross sections twist what normal stresses are generated. I hope that answers the question. I kind of fumbled a little bit, but but you're reflecting what's going on in a cross-section when it twists with respect to normal stresses via warping only.
Okay. Next question, do you need to interact the bending stresses and torsion in this example?
According to AISC, it's just rote superposition. So we are interacting the stresses, but since we're limiting what's going on to yield and below, we're in the elastic range, and because of that, it's a pure superposition problem. So are we considering, if the question is relating to second order effects possibly, which I don't think would apply here, but if it's relating to second order amplification, what's going on from interaction of twist and bending, that's ignored. Again, I don't think there would be much, but we are kind of interacting those things just by adding up the stress effects. And again, really that stems from limiting everything to yield or below. So I hope that answers that question.
Okay. All right, thanks, Dan. We're pushing quite a bit over on timing here, so we're going to wrap up the Q&A. We've got some questions we didn't get to. I'll work with Dr. Linzel in the Solution Center to address those questions that we didn't address today. So, one last